Hey, good afternoon. Today is kind of a short stream, I guess, I hope. It's all about the ZX Spectrum 128K Plus, so also known as Toastrack. Many people know that Toastrack has a weak clock signal, and that's because it's not buffered when it goes to the edge connector. So it's the signal created by the ULA chip, and there's nothing in between before it's getting to the connector where you can connect anything to it. And that wasn't really a problem until recently, because George Philosoph developed the KMOS Turbo interface, the newest version, so the 2070 version. And this one actually has three throughput edge connectors, as you can see, so the back one and two on top, the vertical ones, which is quite neat. But it creates a problem, and I've been discussing this and digging into if it's really the cause of the issue. It adds a long track to the clock signal, and that is causing a problem on the Toastrack. So what we're going to do today is to find out what the best solution is to get rid of that problem. And there are actually two, but first let's see what happens actually. I hope audio is okay. Let me know if anything is wrong. I can also, of course, always restart the stream, but I think everything is okay. First, let's see what happens. So let's get to the test corner, and you will see that when I connect it this way to a Toastrack, it won't boot. When I do the same with a +2 board, it will be no problem. So let's do it. So here we are. Let's see if you can see everything. Yeah, I think so. So this is a Toastrack. It's a Toastrack board. It's an unmodified board, so it's an original one, as you can see. Nothing really special here. It boots up just fine, but when I connect this KMOS Turbo interface, this happens. So it doesn't boot. And I could do measuring with the oscilloscope, but I know it's a clock signal right now because I've been doing some checking already. But let's connect the +2 board here. I will show you what the difference is. And the +2 has a added double buffer before this clock signal goes from the ULA chip, which is underneath here, to the edge connector. And this way, the machine boots up just fine. So let me plug in a mouse, and I will show you that the mouse interface is now working just perfectly. So I will show you the value of the x-axis. So, and as you can see here, it's just running completely fine. So no problem on a +2. So to make sure it's really the clock signal, the easiest thing would be to disconnect the clock signal from the KMOS Turbo and see if that makes a difference. So let's do that. So we know it works on the +2, there's no reason to keep this here anymore. This is my board rack where I put all my machines in. Boards in when I don't use them. So let's get back to the other side. Hey, and good afternoon. And let's get working. So, the clock signals, the pin is right next to the two ground pins here, so that's an easy way of getting it disconnected. And I'm just lifting it up a bit. From two sides it seems, because it doesn't want to. So it's lifted up now. It's not connected. I'm double checking, but it's not connected to the board anymore. And now the question is, of course, will it work? So let's get back to the test corner. And actually the KMOS Turbo is not using the clock signal. That might be part of the problem, because if it was using it, it was kind of terminating the clock signal on one of the chips that it uses. But it's not, so that's the issue. So what do you think? Will it work or not? I know it will work because I've tested it already. Let's do the same test with a beautiful bronze keyboard here, a test keyboard. Oh, oh, that's the joystick port, of course. 6, 4, 4, 7, 9. That's the x-axis. And same result, this works just fine. So once we disconnect the clock signal, we know for sure that the interface is working. So we have two options now. Well, the first option would be to try to terminate the clock signal on this board. And we can do that using a resistor maybe a resistor in combination with a capacitor that will act like a delay or something like that. But it will influence the clock signal then, and that's not what we want. We just want to make sure that there's no capacitance between it, building up between tracks on the board. That's the reason that we want to terminate the signal. It's kind of a known practice in the past when you use the SCSI devices. They needed to be terminated. The last device needed to be terminated, and sometimes they hadn't built in the termination, and it was just not more than a resistor network, resistor bridge on all the signals. So we can try the same. We can add a resistor and see if that makes a difference. The other solution would be to actually add the buffer that's the same circuit as within the +2, but there's no space on this board to add it easily. I could use, for example, a very small single gate low voltage buffer, non-inverting buffer, but I have to do that on a separate board, and if we can do the termination on this interface itself, I think that would be a better solution. So we will first try that, and now the question is, where should we put the termination? It should be at the end of the board, but the question is which end, because we have a back end with two top ends, so the clock signal goes to each of those connectors. So that will be kind of hard, but I think the best thing will be to just put it on the back, on the edge connector that goes to the back, and solder the resistor underneath there. And because it's right next to the ground signal, I think it would be best to put a 10K resistor, for example, to try in between ground and clock. And we can use an SND transistor for that. Otherwise we can use a full transistor, but we have both options. So I think we'll start with trying to add a 10K SND resistor between the clock signal and the ground on that board. So let's try that. So I could use a 1206 component size or something smaller than that, and now I will try the 0805, which is a bit smaller, and I think that might be the best size to put in between. Oh, yeah, so it's there. Don't think I'm not sure if you can notice it, but it's really there. So we're going to actually try to put it in between those two signals, and I'm not sure how easy that will be. Maybe it's a good idea to just get off the solder between those pins first. And I think we will have enough space then to put it between there. Not completely sure. Maybe I should use a 0602 type, but I think this will fit. Or doesn't it? It barely fits, but I think I'm just going to put it right next to those two contacts, and there's still enough space there, so let's do that. So not actually between there, but let's see. What is the best option here? Maybe I should just pick the smaller one, the 0602. I think I have them, but... And there are some customers that experience this problem as well, hence I'm digging it out, what the issue is. Ah, look, it will fit if I put it in this way. And this is good enough. You just have to touch those two pins, there's nothing more to that. So this is good enough. Let's try it again. Oh, the tweezer's not helping me at this moment. We're going to try it and put it in here. Ah, this must be it. Just stay there, and we're going to solder it and see if this will help. And of course we have to solder back the clock pin that we just disconnected in the previous work here. So let's solder it back. So we added a resistor only to pull down the clock signal, and it may cause even more problems, but it's somewhat of a termination, so we can try that. Let's see what it does. Nope, that doesn't work. Alright, no luck there. So, putting it down doesn't help, and maybe putting it up. So I'm going to use another 10K, but this time I'm going to use a through-hole component. And then we're going to try to connect the clock to 5 volts by 10K. The 5 volt signal is on the other side of the slot pin. First let's get out that one here. So there might be a better way, maybe I should use a capacitor instead, but that's a completely different way of terminating something, so I'm not an expert in this, I'm just trying to make it work. And let's see, I think 5 volt is the second pin from the slot pin. Let me check on my documentation. Edge pin out, ZX Spectrum edge pin out. So this document here, so it's the second one from the slot. You can see the slot pin here, and it's the second one. Otherwise we get to connect it to 9 volts, and that's not what I want. So let's get to the second one then. And I'm not allowed to touch anything else, of course, so I have to be careful. How will I do this properly? Oh, I just dropped this. I think I will get another one anyway, but oh, maybe we can just put it in between the 2 rows here. Yeah, that's a good, cool idea, I think. Let me check if it's long enough. Yeah, that must be it. Okay, put this away. Just experimenting and see if this works, but I don't want to mess it up by creating a short, of course. So let's see, there's a second pin here, and this is about the angles, the space that we need. Yeah, I like this. Now cut the pins to the correct size. Right. So there's a resistor now on the correct pins. I'm going to connect it with solder. That's one. Oops, dropped some solder on an edge pad. We don't need that, so we have to remove that. I'm still using 10 kilo ohms, which might just help with the issue. Alright, so connected to 5 volts. Well, let's test it again. Let's see if this helps. So this is actually just a pull up resistor now, and still doesn't boot, so that doesn't work at all. Now the next question is, can we use a capacitor? And now the question, I have no idea if you can use a termination capacitor. I'm looking in Google. Let me open my document, because I already created a document with some hints for myself. So maybe there's something in there. So I'm actually looking up the way that SCSI ports are terminated, and those are just terminated by a resistor, so that's not helpful at all. I knew that already, just wanted to know if there's any capacitance there. Nope, so that won't help. Alright, so this is not the best way of doing this. Use a cap. Okay, Janze says use a cap, 10 nanofarad. Okay, I want to try. But again, I'm no expert in this kind of solution, so We can try 10 nanos. Jan, would you do that to ground or to 5 volts? I think the ground. Oops, I just damaged the magazine here. So just a second. I will use a SMD capacitor, because if we're going to do it to ground, I think the best is to just put it in between. 10 nano. Like I said, I'm not sure if the location where I'm trying to put the capacitor is the best location for it, because there are 2 more edge connectors that will spread out the clock signal. Okay. Okay, it's connected to ground, so very simple SMD one. Let's see what that does. Still nothing. So, I'm afraid it will not be a proper solution. I'm afraid we have to get to plan B, which is getting the buffer circuit ready. And first I want to check out what chip is used in the +2. I think it's an HCU04 in the Z-Expression +2. Oh, I'm still wrong camera here. So, yeah, remove the resistors. Let's get into the circuit of the +2. And we'll show you in a second. Right. So here's the +2 circuit. And you can see that it's using an HCU04, so 74 HCU04. And I wonder what the differences are between the HCU and just the HC. I don't know that, so I'm really interested in that. 74 HCU versus HC. I'm not first asking that, so I wonder about that. Alright. What is a HCU4? Alright, this is interesting. So I found a forum here. Let me open it up. It's a bit small, maybe we can zoom in. Yeah, we can zoom in. Okay, so HCU, CMOS input switching levels 2080. What's the difference between that? Okay, it's usually 3070, so it's a bit different from a HC chip. So it switches at other levels, and I do wonder if... Okay, unbuffered outputs to allow operation in linear mode. Supply voltage between 2 and 6 volts. Okay. I really wonder if this will make a difference, and the reason I say that is that it's because I think I've seen HC chips as well on a +2, and also we use HC in, for example, the Harlequin kits. So I guess we can try the standard CMOS type for this. I'm not entirely sure. So what shall we do? Shall we first... Should we try it with an HC? I think it's a good idea to use a breadboard. Let me think about which one. Let me think. How can we do this the easy way? So I need an extender board, and I think I have one, so let me grab it. It's in here. It's on the back. I can't reach it. Sorry guys. Look, this is the idea I have anyway, so we can use this board and we can do some experimenting with this one. I made some other stuff here, for example, a simple plus 2A plus, oh man, plus 3 fixer board here, so with 2 diodes in the back, but of course this is just an experiment as well. But I've bought more of these, you can see here. So we're going to use this one, and what we're going to do is we will just add a HCO4 to make sure that the HC is working as well as an HCU. So that's what we want to know, and I'm going to use just a dip version of that. And we'll wire wrap, so I'm not going to spend a lot of time on it, just want to make sure it works. Okay, so I have some HCs here, but also there should be some HCUs in here. Let me check. This is an LS. This is an HCU from, I think, an original Spectrum, so... Okay, LS, another HCU. And I have plenty of HCs, by the way, but they're in a different place here. So let me get the HCs. And then we'll get a socket. So this is a 14-pin socket. And we'll wire wrap and see if that works. Let's get rid of the SMD components again. Alright. So, let's first detach the clock signal again on this test board here. So this will be the experiment board for this clock buffer. That's what I'm trying to achieve, and the good thing about this is that I can just offer it separately if someone uses a Toastrack, for example. And you can think, you may think that it should be solved on the KMOS, but I don't think so, because it's really a Toastrack problem. So even if we would add something to that board, but it's a lot of work, by the way, creating a new version of that, because there's no space on the board anyway. It still is only Toastrack specific, so I'm not entirely sure of doing that. But anyway, let's continue. So we want to know if the HU and HC04 are both working here. So we're going to wire up this socket. I need some long wires, and also I think, if it's possible, I want to use a red wire for power, and I want to use a orange and a yellow wire for the clock signal coming in and going out, or white maybe. White's nice as well. We have a thinner orange wire here. Yep, I have thinner wires. I like thin wires for this test, just for a test. So we have 4 thin wires, 4 colors, and that's enough. We just need 1 port of the HCO4. That's easy. Let me grab a data sheet of that. So 74 HCO4. So that would be simple. Let me open it up in a new tab. Yep. So what we're going to do is we're going to wire this chip here. Let me zoom in. And only use 1 port, for example, pins 1 and 2. Oh, sorry, this is a 04. Okay, we need 2 ports actually, because this is an inverter. So this is what is used in a +2, and because it's an inverter, we need to double invert it, so we need 2 ports. We can connect pins 2 and 3 to each other and use pin 1s and 4 for input and output. That's what we're going to try. So first, let's connect pins 2 and 3, just like we said. I think I will just do it quick and dirty, because we want to know it works. I hope this video is not for nothing. I really want this to work. So hoping the best that this will be a solution. And of course, it would be bad to create long wires to the clock signal. So for the input, I will use a short wire, and for the output, it doesn't matter really. The only problem is it's on the bottom of the board, so they got to be a couple of centimeters, you know. So let's do it this way then, and let's see if it will help. It's about 4 centimeters each. Oh, sorry, wrong camera. Right, we're here. And one more wire, and that's all, I think. And good thing about the single gate solution, which is not inverting, so that would be an HC7, for example, HC07, is that we just need 4 pins to connect on this very, very small chip. So that would be the best solution if this will work. But because it's also CMOS standard levels, we want to make sure that it will work with a HC chip. That's what we're going to test here. You can imagine what I'm trying to achieve. Right. Okay, so we have an input. I think what shall we do? Orange or white? Doesn't matter really. So let's take the orange as input, coming from the zero spectrum, and let's put the white to the throughput edge here. Right, then we need ground, and we need 5 volts to feed this chip. So far so good, nothing ridiculously difficult here. 14 is of course 5 volts. Oh. Pin 7 is ground. Right. So let's do the input. That's the orange one here. Input goes to pin 1, as I said. The output is the white one that goes to pin 4 after the double inversion and buffering. And then the black one goes to pin 7. And the red one is going to pin 14. Alright, so this is all. This is what we need. So we will put in a HU4, so that's known to work with this setup. The only problem that can still remain is that the distance, the added wire length messes up the clock signal already. So that's what we want to get to know for sure. But if this will work, and even with the HCO4, so this one for example, then we know that the single gate solution will be a solution as well. But first let's try this. I'm not sure if, by the way, if these chips are okay, but I guess they will. So let's get to the test corner again. Oh wait, I have some software running in the back, so let's stop that. So I'm not sure how the video quality was until now, but it was doing something in the back. Alright, so let's get to the test corner and see if this helps. But where did I leave my K-mouse now? Oh, there it is, sorry. So before connecting the K-mouse, first let's see if this works. Okay, without any interfaces it works. Let's add the double buffered clock buffer. Nothing wrong with this. Let's connect this and see if it still works. Yeah, this is perfect. Nothing wrong here. And now let's see if the K-mouse works. Yeah, so that works, and that's nice. So the next thing is, well, let's first do the simple mouse test and see if it helps. So we double inverted and buffered the clock signal, and this seems to work just fine. So that's okay, but we are not using the clock signal on the external interface, so that's what we don't know yet. So we still want to know if the clock signals can be used on an external interface. Okay, the mouse works just fine. So the next thing is to use an interface that actually uses the clock signal. And for that we need a older diffMC interface, for example this diffMC Enjoy Mini. This is not the Pro Mini, which doesn't use the clock signal anymore, but this is an older version. And we're only going to connect it to Toastrack and enable ESX tools, but not do anything else. So let's see if this works. It boots, but it cannot find a clock signal, I guess. No, it doesn't have a proper clock signal. So let's get the cameras out in between and let's see if this works. For some reason it doesn't want to find the card, and that means that it's not getting a correct clock signal because it relies on a clock signal. So for some reason this doesn't work. Why not? Because it's the same solution as on A+2. Nope. And I bet a normal diffMC will work because this one doesn't rely on a clock signal. Okay, so that's too bad. This works just fine, so that's too bad. For some reason this doesn't work. And maybe it's just the chip that's dead, I don't know. So we have to investigate it. We can try another chip. And maybe I have a working one from this board, let me check. I guess it's soldered. Where is it? Ah, look, it's here. So this one is a known working one, so I think it's a good idea to use that one. It's socketed already. I would like to know that. So I'm putting that one and we'll probably put it in here. And see if that makes a difference. I don't see any reason that this wouldn't work, so I really wonder what's going wrong here. Oh, let's put it upside down instead. Fortunately there's a slot pin here. Alright. Okay, it's still booting up. Now let's connect the diffMC again and see if that helps. Oh, just disabled ESX accidentally. Still no luck. So I wonder what is going on here. Let's investigate the +2 schematic again. Oh, I think I know what's going on here. I think I know it. But I'm not sure. Let's compare the two schematics. Let's get back here. Alright, so let's get the schematic of a +2 and open up. And also, yes. And now let's get to schematic of a Toastrack and see what we might be doing wrong here. Yes, okay. So this is the Toastrack schematic, and you can see here that the clock signal from pin 39 is going directly to pin 8A on the edge connector. So nothing like buffering or something, nothing. And there's only one transistor that will buffer the clock signal and invert it before it goes to the Z80. But the +2, is it here? Yeah, it's here. Actually does double buffering. So it first buffers the signal before going to the Z80, and then it buffers it again before going to pin 8A. So we actually did exactly the same as done here. So we used an HU04, connect pin 2 to pin 3, and use pin 1 as input and pin 4 as output. Let me check again. Double check. So let's see. We're doing the input to pin 1. We connected pin 2 to pin 3 and then use pin 4 to get back to the board. So that should work, but it doesn't. For some reason. Maybe it should. I don't know. What could we do? I don't know. I'm out of ideas at the moment. Am I using the correct pin for 5V? I could measure it, of course. But I don't think that will be the issue. We're using ground. Let me double check. Do I still have that open? I don't think so. So here's the edge pin out. So we're using 5 volts, 2 pin 14, and ground 2 pin 7. So I really cannot find what's wrong here. So here's the schematic again, sorry, the diagram of the chip itself. What are we doing wrong here? I have no idea. This should work. So I only can imagine that the wires are maybe too long or something. That's my best guess. So that's also not completely working as we want. Okay, the next thing should be to measure the output and actually see output and the input with an oscilloscope and see if that will is actually different. So can we do that? Let me check. I think that would be the best to do next, because we want to see if the clock signal is correctly buffered and we get any output. Otherwise there's nothing to check here. I think we should do that. So let's get to there again and get the scope out of its stored space. It's getting a bit of a mess here, but too much stuff. Not much space, but we'll manage. Alright. See if you can see the scope. Yeah, you can see the output here. Why is it not leveled? It is now. It's still not leveled. The cable on the back. Okay. So let's measure the clock signal and see what's going on. Put it in here. Let's get the keyboard up. We don't need that at this moment. And connect ground first. If the probe wants to help me out. So, sorry. Okay. And can I turn it? Yeah, I can turn it. Okay. It's a bit short, it's a bit unpractical, but we'll manage. Alright, so first let's connect it to the clock input. So that's done. Fire it up. And press auto to get it on screen properly. Right, this is the standard clock pulse. Can I make it more stable? No, not really. Alright, so now we want to check what the output is. Nothing. There's nothing on the output. Why not? What am I doing wrong here? So we do not get any output. Let's check pin 2 and 3. There's something, but it's messed up. There's something, but it's a very weak signal, almost 5 volts. So that won't work. And we are actually using an HCU04, so I wonder what's going on here then. I don't know. Let's get back to the schematic. No, there's no short. Okay, let's think. Let's get back to the Toastrack schematic first and see if we can find anything. This is the +2 schematic. Alright. So I'm really wondering if we're missing something here. Oh, there's a pull-up, 1K5 pull-up. Oh, that might be a reason. Okay. There's a 1K5 pull-up on the +2 coming out from the ULA chip. And I don't think that's present on the Toastrack. Let me check. ULA, yes. It's a different circuit, as you can see, but it's only on the base of this transistor, so I don't think that's the same. Oh, wait. There's actually a transistor R73. Is that the same as the other one? Oh, R73. No, it's a complete, of course it's M-Strat, so it's completely different. But there's no value here, that's a pity, but of course I can check. But there's actually also a pull-up here, so I don't think that will make much of a difference. So what else could it be? Could it be that this capacitor here, C67, is influencing the output of the ULA chip together with the 100 picofarad? That could be the reason. But otherwise I don't know. I really don't know. What might be the difference? What might be the difference? Could it be the R73 is a completely different value than the one in the +2? So we can check that, of course. So I'm grabbing the board. Which one is that? Is it clear on the board, or do we have to start guessing? Let me grab a multimeter. Oh, let's switch. Right. No, this HCU04 is coming from a working +2, so that's not the issue. I still don't know. I still absolutely have no idea what is going on here. Okay, let's find the transistor that we're looking for. And it should be close to pin 39, or it should be connected to pin 39 because it's a pull-up to 5 volts. Let me check it on the schematic again. It's R73 that we're looking for. So pin 39, do I have a pencil here? Where's my pencil? What are it? Okay, so this is 24, 5, 6, 7, 8, 9, 30, 41, 42, 43, what was it? Okay. 4, 5, 6, 7, 8, 9. So it's this pin here. That should be clock. And we can check it. Make sure that it's the correct one because it should go to the, what was it? The white or the orange wire? The orange wire. Our orange wire. So that's for sure the clock signal going directly from the ULA chip to the edge connector. And now the question is, which resistor is connected to this? So which one is it? Which one is it? Where is it? I can't find it. I think it's this one, it's a 1K. And if it's this one, the other side should go to 5 volts. And that's not true, that's not the case. Oh, okay, this is R24, so this is not the correct one. I still wonder then where it's connected to. Should be another transistor, resistor somewhere. I don't know. Oh, sorry, dropped it. 73. Oh, wait! Ha! Get out of here. This is ridiculous. So, on the schematic it says it should be here, but it should be here. There's no transistor here. Sorry, resistor. Sorry for my speaking mistake. Okay, so there's no resistor here. Why not? Okay, so it's not present here, but the only thing it does is connecting the clock signal coming from the ULA chip to 5 volts. And we can do it on my experimental setup, so I think best is to try that. 1K5. Let's grab one. So it seems that Sinclair really was trying to cheap out on this. That's interesting. I like interesting finds like these. I never expected this, but anyway. So that pull-up is not present, and that is making, of course, a huge difference to the signal. it's a kind of a small pull-up. It's a 1K5. It's not a big resistance. So it's a small resistance. That's what I mean. So the pull-up is bigger because there's a small resistance. Okay, not being very clear maybe. So I want to put it in here. I think I will put it out for a second. That's a bit hard, of course, because the wires will get loose from the socket if I do this. I hope we can manage to keep them on, because I'm just trying a quick and dirty solution for this experiment. So there's still hope. That's mainly the most important. That's the main thing. Okay. Let's grab some tweezers, and this will be frustrating because I know that will come loose, but we'll try this one. Okay, that's one. Yay, we did it. Now the second one, orange is the input, and we still want to try to connect it to the input of the chip. Right, that's quite neat. Nice. So, next attempt with the added resistor. I really wonder if this will work. And I'm not fooling you guys, I really don't know if it will work. I really don't know if we'll have success. So it's just an experiment and I don't have that much time, so I really hope it will work soon, because I have some other stuff to do. So we're going to use the oscilloscope again, because that gave a good impression of if it will work or not. And I'm going to measure the pin 2 and 3 first again, because that will show if it works. Yeah, the signal is a lot better than we had it before. So the 1K5 is really doing its job now. Let's see if we get a clock output on pin 4. Yeah, we get a clock output. Okay, so that was one problem here. You can see it on the scope, I guess. Oh, almost not. Let me move the scope a bit. The power cable is too short. We'll see if we can change that. We actually can, so it's not a big issue. I think it's, is it better? No, it's not. Okay, just a second. Let's do it this way then. We have enough space here, it's just all the cables are messed up. So I want to be able to show you exactly what we're doing. Okay, now you have a clear view on the scope. So this is the output of the chip on pin 4. So you see now there is a clock signal. It's kind of small, but it is a clock signal. So this will mean that if I connect a old different C interface, that it will now just boot without any issue. So let's see if that actually works. Oh. So this is not the goal we're aiming for, but because if you ruin the clock signal, if you don't have a clock signal, well, what will you use the throughput edge connectors for then, of course? Let's see what it does. Yeah, and it works. Okay. Oh no, not completely. Too soon, Ben. It gives an error. Let's try another card. Too bad. No, same thing. Let's try another interface. Do I have another standard one? I had another one, did I? I have 4, or do I just have 3? I will have more here. I'm just not sure what the status of this one is. So I only want to enable ESX DOS and disable the joystick interface because there's no joystick chip on it. This is an older one. Okay, let's try this one then. It's not doing anything. Why not? Dirty contacts. No. Same issue. So still an issue with the clock signal. I don't know what it is, but there's still an issue. So what can we do then? Well, I'm curious how the signal looks on a +2. So I want to know about that. And now I want to know how the signal looks like when it gets into the Z80, for example, which is the double buffered signal. So let's see, let's connect it and let's measure pin 6 of the Z80 CPU. And let's get a grab on a ground pin first. Where do I have a ground pin? I think here's a ground pin. Yep. Alright. And now let's try to connect it to pin 6, which is kind of hard because I have some odd replacement board for the PHF chip here, but I think this will all work. 1, 2, 3, 4, 5, 6. So let's see what output is here. So here you can see the output is much more 50-50. And I really wonder what could be the difference. So this is clear that it is a more proper clock signal. And if I put on a DivMC old version here, I guess it will just work. Nope. I hope I'm not messing up this math here. We'll see. I still want you to get to be able to see the clock signal. Yeah, I think we'll manage. Right. So you can see it's working, and it really depends on the clock signal. That's for me, it's totally the cause of all these issues. So what is the difference between this and what's going on this board? Even because if you think of it, ULA's chip is here, the HU04 is here, and it's all routed through completely over the board to the edge connector. So what could be it? We know this is a working chip because this is the one that I just pulled from this board, but it's still different. So there's a difference in the output, and I really wonder what could be causing that. Why is the output different? So we use the 1K5. Is there actually a 1K5 on this board? I think so, but I want to make sure, because maybe they use another value. That could be cause, of course. It must be something like that, you know. It's something like when how the clock signal, the exact timing of the clock signal. So the rising edge and the falling edge. That's what we need to know. I think it's this resistor here. It's a 1K5. So let me check. It's R81 on this board. I'm not sure. Let me check. So let's get back to the schematic of the +2. And the pull-up is R101 on a +2. So which one is that then? R101. R101 going from pin 1 of the chip. I really don't know. So it's not the R81 underneath. It should be R101. And I'm hoping that this is an issue 3 schematic. Yeah, it's an issue 3 board. So it's the board I'm looking at the moment. So it should be R101. Let me get back to the circuit here. R101. It can be anywhere on the board, of course. Well, no, it can be because it's coming from pin 39. So it must be close to pin 39, I guess. Why am I not seeing it anywhere? Dang it. I don't know. Can't find R101. Do I have a board? Do I have a board? Board layout. Let me check. No, I don't. I have a technical manual. Is the board layout in there? Let me check. Of the this is a Toastrack. I don't need that one. I need the +2 version. Layout. Yes, we have a layout. Oh, this is perfect. That's exactly what we needed. So can we find R101 on this? Where is R101? I should watch the chat at this moment because maybe you already found it. It's not near the ULA chip, is it? No. That's odd. It's not there, it's not there. So that's odd. Let me check the chat. Maybe you've seen it already. Check on solder side. Oh, of course. There was a note that it could be on the solder side. You're totally right. And it is! Haha! You're right. It's there. Okay, so hence it's not on the board layout. Oh, I'm so stupid. Okay, you're totally right. So I read it, but I forgot it. And it's between pins 1 and the 5 volts. Exactly what we are expecting. Let me grab my board. So what is the difference then? Because these are both the same value. They're exactly the same value. So what am I doing wrong here? Between pins 1 and yeah, okay. I don't know. I don't know. Oh, what could be it? Well, we're mimicking the same clock buffer circuit on that's on a +2. And on a +2 there's a 1K5 resistor pulling up the clock signal coming from ULA chip. I want to make sure that's the case here because you never know. Let me 25, 6, 7, 8, 9, 10, 30, 31, 2, 3, 4, 5, 6, 7, 8, 9. So that's the clock from the ULA chip. Okay, that goes to pin 1. Yeah, exactly. That well, that's exactly what we want to know. So it's really the pin, the signal coming from pin 39. It goes to pin 1 of the HCU04. There's nothing in output anymore. Nope, there's nothing going to the output. I really don't know what's going on here. We created exactly the same solution here on this test board, and it's not doing the same. So what could it be? I don't know. Could it be that the signal going to the Z80 is influencing the clock as well? So what I'm saying is, so it comes from the ULA chip here, pin 39. It goes to pin 1 of the HU04. It's being pulled up to 5 volts. Yes. And when it's inverted once, it's going to the CPU. Let's see if it does anything before getting into the CPU, pin 6. Okay, there's a 47 ohm resistor before it's going into the Z80. I don't think that will make a difference, but I'm not sure, of course, but I don't think so. So, I'm still puzzled. But I have a problem. I have to go out in a couple of minutes, so I have to get up soon, or actually no. If you have any of these guys, please let me know in the chat. I think we did our best until now to find a solution, but I haven't found it yet. So if you have any more ideas, I will check it out later, but I have to go, sorry. So we'll speak to you later, guys. I hope we can figure it out. So thank you for watching again, and see you tomorrow, maybe, or otherwise on Monday.